This is a review of friction and forces in two dimensions. Let's take a look at number 90. We're given the mass of a box that we're sliding across the floor. The first thing I'm going to do is draw a free body diagram for this box. So in the up direction we have the normal force. In the down direction we have the force of gravity. To the left we have the force of friction, because we're sliding something along the floor, and to the right we have the applied force. My directions for the force of friction and the applied force are arbitrary. I could have made the applied force to the left and friction to the right, but generally we like to say things are moving to the right, so I put friction to the left. It says in the problem that we have constant velocity, which means that there is no acceleration. And remember that if there is no acceleration, that means that there's no net force, which means that the forces must be balanced. So we don't even need to use Newton's second law for this one. We just know that the applied force is going to be equal to the force of friction, and the normal force is going to be equal to the force of gravity, because there is no net force, because there is no acceleration. So we know the applied force, that's given, and so the force of friction must be equal to that. Remember that the force of friction is equal to the coefficient of friction, which is the Greek letter mu, times the normal force. The normal force is mass times gravity. So we can set 30 equal to mu times mass times gravity. We can plug in some numbers and we can solve for mu, and we can get our answer. Number 91, we are given the mass of a different crate, and we're given the coefficient of friction. Let's get a free body diagram here. There's an applied force to the right, the normal force is up, the force of gravity is down, and there is a force of friction to the left. So it says in the problem here that we do have an acceleration. I think it's asking you to calculate the acceleration. So the forces must not be balanced. If there is an acceleration, the forces are unbalanced. And whenever they're unbalanced, we can use Newton's second law, which says the sum of the forces are equal to mass times acceleration. So the sum of the forces are the forces to the right minus the force to the left equals mass times acceleration. I know the force to the right, that's given. The force of friction I can calculate. Let me stop there for a second. I can calculate the force of friction because I know that the force of friction is equal to mu times mass times g, which is 9.8. You can set that equal to mass times acceleration, and then you can solve for a. Again, that expression in the middle there is the force of friction, which can be calculated by taking the coefficient of friction, multiplying it by the mass, and multiplying it times the acceleration of gravity, which is 9.8. Number 92, we're given a block on a horizontal surface. The mass of the block is given, and the acceleration of the block is given. Let's take a look at our free body diagram. It should look familiar by now. We have an applied force, the force of friction, the normal force, and the force of gravity. So we have unbalanced forces here because there is an acceleration. The forces are not balanced. So that means that there must be some sort of net force acting on the system, which means that we can use Newton's second law. The sum of the forces is equal to mass times acceleration. The sum of the forces is the force to the right minus the force to the left equals mass times acceleration. We can plug in some numbers here. We know the force to the right minus the force of friction must equal mass times acceleration, which are both given. So then we can calculate the force of friction. Now, the question is asking for A, the force of friction, we just found that, and now B, the coefficient of friction. So let's look at our equation for the force of friction. We know the force of friction is equal to mu times the normal force. We know the normal force is mass times gravity, 9.8. So let's plug in our numbers here. We can divide and we can solve for the coefficient of friction. Number 93, we are trying to move a refrigerator. We're given the mass, we're given the coefficient of kinetic friction, we're also given the coefficient of static friction. In order to move a refrigerator that is at rest, that means you are overcoming the force of static friction. The word static means still. So we can ignore kinetic friction in this problem, because we're trying to move a refrigerator that is at rest, which means we must overcome the force of static friction. So in order to move the fridge, the force that you are applying must equal the force of static friction. So in order to find the force that we are applying, let's take a look at the force of friction. We know all these things. We know the mu, we know the mass, we know the acceleration of gravity. so we can calculate the applied force rather easily here. Again, I'm using the coefficient of static friction because the fridge is at rest before we try to move it. Kinetic friction is only for things that are already in motion. Let's take a look at number 94. We're coming to rest in a car. We're given the mass of the car, the velocity initial before we brake. We're given the distance before the stoplight, and that's asking for the coefficient of friction. So what do? Well, we can't find a force without an acceleration. So when you come to problems like this, where they give you very few knowns and lots of unknowns, and you don't really know where to start. We know we have to deal with forces because we're given a mu here. It's asking for a mu. So we need to find the force of friction. In order to find any sort of force, you need to calculate the acceleration. So take a look at what we're given and see how we can find the acceleration. Well, we can use one of our kinematics equations. We can use the Vf squared equals Vi squared plus 2AD. Remember that we're coming to a stop, so the final velocity is going to be 0. I rearranged here for A. I plugged in the numbers, and my acceleration is, I should have put a negative there, I forgot the negative. It should be negative 3.92 meters per second squared. Okay, now that we have our acceleration, we can enter into the land of forces. So let's take a look at our FBD here. The only horizontal force is to the left. What happened to my applied force to the right? Well, think about it. There's nothing applying a force to the right of a braking car. The car is moving to the right, but it's slowing down. And there is no force of the engine because you've taken your foot off of the gas pedal and you've placed it on the brake pedal. So the only force in the x direction is the force of friction to the left. And then of course we have our normal force, and of course we have our force of gravity as well, which are equal and opposite. We know the sum of the forces is equal to mass times acceleration. There, it looks like I forgot my F. So in this case, we just have the force of friction, the minus force of friction, equal mass times acceleration, because there is no applied force. Let's expand the force of friction here. We have mu times m times 9.8 equals mass times acceleration. So before I even plug numbers in, I'm going to cross out my m's. Okay, so now we can solve for mu by doing some division here. The acceleration is exactly what I found in the first part. Again, I had forgotten to write the negative the first time, but I wrote it in there the second time. So your negatives turn into a positive, and then you get a positive value for mu. Remember that mu is a coefficient between 0 and 1 that is always positive. Number 95, this is these problems are forces in 2 dimensions. Remember what the word equilibrium means. Equilibrium means that there is no net force, which means that the sum of the forces are equal to 0. So we're given a couple things here. We're given, let me stop there for a minute. We're given a force in the up direction, straight up, 33 newtons, and then we're given a force at an angle. We can't deal with angles. Now here's why. The math that we use, our kinematics equations, our algebra, only works for motion in one dimension, either the y dimension or the x dimension. Our math doesn't work for angles. So anytime we have a vector at an angle, we have to resolve that vector into a single x component and a single y component. Then we can use our equations. So as soon as I see this 44 Newton vector, I'm automatically thinking, all right, I got to put it into an x component, into a y component before I can move on. Using my trig functions, I know that the x component is 44 cosine of my angle. I know the y component is 44 sine of my angle. If this trig is unclear to you, take a look at a different video I'll put up about how to use trig for these problems. I went ahead and put this into my calculator here. So I know that I have a force in the right direction of 22. I know that I have a force in the up direction of 33, and I have another force in the up direction of 38. So in total, I have 3 forces. And again, I can't deal with things at an angle, so I have to put these just in terms of x and y. Okay, now that I have my total forces to the right and my total forces up, I can start to solve my problem here. So I added my 2 forces up, so I have a net force of 22 to the right and 71 to the up. You know what? It looks like I did that wrong, didn't I? I did it to the left there instead of to the right. I should have done it opposite. I apologize for that. But you can. Oh, you know what? No, I didn't do it wrong. I'm not reading the question. Excuse me. The question is, what force would cause it to be at equilibrium? Okay, here we go. So we're looking for the force that would make it equilibrium. So on the left here, I have the forces that we already have. We have a 22 force to the right and a 71 straight up. So in order to make it at equilibrium, I must cancel out my forces. So I need to have a 22 to the left, and I need to have a 71 down in order to cancel out what I started with. And then if we draw a resultant force tail to tip for my new x and y components, I can find the resultant, or the hypotenuse, to be 74. In order to find the angle, you can use your inverse tan function. You can really use any inverse trig function to find your angle there. Let's take a look at number 96. We have a collection of forces in different directions. I sort of laid them out here for you so you can sort of visualize how they're added up. And then we're given a force at an angle. Forces at an angle, we can't use our math with forces at an angle. Anytime you have a vector at an angle, whether it's a force or a velocity or whatever, you need to resolve it into its x component and its y component using our trig functions. Y component is 50 sine 60, x component is 50 cosine of 60. Let's put some numbers to it. Now I'm going to go ahead and add these vectors up top next to the other ones. So I have a complete collection. Up at the top I got 1, 2, 3, 4, 5, 6 vectors, each pointing in either an x direction or a y direction. So now I can add them up. So we got a 43 to the up, we got a 60 to the up, we got an 80 to the down. So that equals a net of 23 up. We got a 40 to the right, we got a 25 to the right, we got a 40 to the left. That equals a grand total of 25 to the right. So I have a total of 23 up, total of 25 to the right. So in order to cancel that out, I'm going to need a 25 to the left and a 23 in the down direction, because the question is which one will make it at equilibrium, zero net force. So I need to cancel out what I'm starting with. So then I draw my resultant vector, and you can find the value of that using the Pythagorean theorem. And you can find your angle using any trig function you like, any inverse trig function. I prefer to use inverse tangent to find that angle. This here is number 97. We have a hanging sign between two buildings. We're given the angle. We're also given the weight of the sign. Remember that the weight is simply another way of saying the force of gravity. So I have an angle here, and I can't deal with that. Angles do not work with our mathematics, so we need to resolve the angle into a y component and an x component. The y component must equal 7.5 times 10 squared. Now, how do I know that? Let's stop there for a minute. If the force of gravity is pulling the sign directly down at 7.5 times 10 squared newtons, that means that in order for the sign to stay still, there must be a force pulling it directly up at 7.5 times 10 squared newtons. That force pulling it directly up is the y component of the tension in the rope. If you take a look at that picture in your textbook, there is no rope pulling it straight up. There's a rope pulling it at an angle. Well, that rope at an angle has two components. It has a component that pulls straight up, and it has a component that pulls straight to the left. The component that pulls straight up must equal the force of gravity, which is straight down. So I know that the component straight up must be 7.5 times 10 squared. Also, the sign the sign needs to not move right and left either. So that means that the tension pulling to the left that I drew up there must equal the tension pulling to the right, which this question is calling B. I know that B must equal the y component of my tension. So, alright, here we go. If I use my tangent function, I know that it will be, oops, excuse me, let me go back. Using my tan function, the tangent of my angle is going to be the opposite over the adjacent, so I can solve for B here. The tension equation, the tension in rope B, which is equal to the x component of the tension in rope A. Alright. This is number 98. We have a street lamp, 2 wires at 120 degrees. That means that each one is 30 degrees. Now, how do I know that? Well, I mean, I don't. I guessed. You can make it however you want, as long as the angles all add up, as long as the angles between your 2 wires are 120. So, for example, those angles that I drew in yellow could have been 29 and 31, and you would have gotten the same answer. I have 2 angles. Our mathematics do not work with angles. So anytime I have an angle, I need to resolve it into its x-only component and its y-only component. So those are the vectors that I've drawn there. The tensions are equal according to the problem. My y component is going to be tension times sine of 30, and my x component is going to be tension times cosine of 30. I'm just filling in my my components here. I know that anytime I have angles, I'm going to need to find the x and y components, so I just went ahead and wrote out what the trig would be for those. Anyway, so what's the problem here? We have a street lamp. It weighs 150 newtons. That means that the street lamp is pulling 150 newtons directly down. So in order to hold it up, my tension must be 150 newtons directly up, which means that the T sine of 30 on the left and the T sine of 30 on the right must equal 150 newtons. So 2 T sine of 30 must equal 150 newtons. So we can solve here. T sine of 30 must equal 75. I just divided by 2, and then we can solve for our tension. So again, the force of gravity pulls straight down. That means the forces pulling straight up must equal that. The forces pulling straight up are the y components of my tension vector. Number 99, we have a box on a plane. Let me draw the force of gravity here. That's given in the problem. Let me stop there for a second. Anytime you have an object on a plane, we generally need to know the force of gravity that's accelerating the block down the plane, or maybe the force of friction that's pulling the block up the plane, or maybe the normal force that's pushing the box out of the plane. In order to find any of those things, we need to adjust our axes to be at the angle of the plane. So I'm going to draw a new y-axis that's parallel to the plane. I'm going to draw a new x-axis that is perpendicular to the plane. I draw 2 x-axes here. I drew 2 x-axes. One of them is actually on the plane to show you why I did it, and the other one I removed further down. The reason I removed that bottom yellow vector downward is so that I could create this triangle. Triangles are helpful. Triangles tell us a lot of things. Triangles allow us to use trigonometry. So the only reason that I have that yellow vector down at the bottom there, the weird one, that's completely out of the picture. The only reason I drew that one down there is so that I can make a triangle, because triangles give me more information that I otherwise wouldn't have access to. But it simply represents the same yellow vector that's up top there. The two yellow vectors that are parallel represent exactly the same value. I just simply removed it so that I could make a triangle, so that I could obtain some more information. The 35-degree angle up there is equal to the 35-degree angle that's given in the problem. I know that because of my parallel and perpendicular line rules. So I can find the force of gravity in the x direction by taking the force of gravity times the sine of 35, and I can take the force of gravity in the y direction by taking the force of gravity times the cosine of theta. So again, the only reason I could do that is because the force of gravity becomes the hypotenuse of this triangle that I essentially just sort of made up. Drawing these new axes allow us to take advantage of the force of gravity as a hypotenuse to find the x and y components. And so I've solved the problem. The problem is just asking for the horizontal component of the gravity, which would be 215 times the sine of 35, and the vertical component of gravity, which should be 215 times the cosine of 35.